Now that we know what the Laplace transform does to certain functions, how to invert it, and what it does to derivatives, let's see how we can use all of those to solve differential equations. First of all, let's recall the method that we know to solve differential equations. So let's say we want to solve a non-homogeneous differential equation, nth derivative minus a1 times n minus first derivative plus a1 times y equals some function of t. With initial conditions y of 0 equals p naught, y prime of 0 equals p1, etc. The nth derivative of y at 0 equals pn minus 1. First we find a general solution c1y1 summed up to cnyn for the corresponding homogeneous differential equation h, which is the same that has 0 on the right hand side. Then we find a particular solution yp to the non-homogeneous differential equation, and then we say that the general solution to the non-homogeneous differential equation is yp plus c1y1 plus all possible solutions of the homogeneous system. Let's say y equals all of this. Then we differentiate y n minus 1 times and use the initial conditions to solve for the constants C1 through Cn. So it's a fair amount of work to do this. Alright, now let me put up the method we're going to use that involves Laplace transforms. So the Laplace transform method to solve the same differential equation with the same initial conditions is much different. So we're going to use this. It doesn't give a general solution, it's just going to solve the initial value problem. So let me say if we don't care about the general solution, so first of all we take the Laplace transform on both sides of the non-homogeneous differential equation. So we'll let capital Y be the Laplace transform of little y, and the Laplace transform of y prime by the derivative rule is going to be s times y minus y of 0, and the Laplace transform of second derivative of y by the derivative rule is going to be s squared y minus s times y of 0 minus y prime of 0, etc. So we'll do that with as many derivatives as we find. Then we plug in initial conditions, because we'll have a bunch of y of zeros and y prime of zeros sitting around. Then we solve the resulting equation. The resulting equation is not going to have any derivatives. It's going to have y's and s's. We're going to plug in numbers for all of these initial conditions, and there won't be any derivatives left. So we'll solve that for y. And that's going to be a function of s. Then finally, we take an inverse Laplace transform, and we're probably going to have to use partial fractions on this. So we'll possibly use partial fractions on y of s to take its inverse Laplace transform. And then this is the solution. So we're going to get the solution to the initial value problem without actually having to pass through the step where we have the general solution with all the constants that we have to solve for. So let's do an example. Now I'm going to take example 10.9.3, or is it at 4? 10.4.3 from the book. And I'm going to do it with much more detail. So the book just has sort of an outline of what you do, but I want to do it with all the details. So the question is, what solution of the homogeneous differential equation y double prime minus y prime minus 6y equals 0 satisfies y of 0 equals 1 and y prime of 0 equals 2. So let's do our old method first. So the auxiliary equation, r squared minus r minus 6, which factors as r minus 3 r plus 2 equals 0. And that gives us the general solution, y equals e to the 3t actually some constant e to the 3t plus some other constant e to the negative 2t. Then we're going to need the derivative too. 3c1 e to the 3t minus 2c2 e to the negative 2t, so that when we plug in the initial conditions, y of 0 equals 1 tells us that 1 equals c1 e to the 0th is just 1, plus c2 e to the 0th is just 1, and y prime of 0 equals 2 tells us that 2 equals 3c1 e to the 0th minus 2c2 e to the 0th. So we have these two equations. And then we can use row operations, or in this case, I think substitution is very easy because we can see that c2 equals 1 minus c1, and we can just plug that in. Or substitute c2 equals 1 minus c1 into the second equation to get 2 equals 3c1 minus 2, 1 minus c1. Which tells us that 2 equals 3c1 minus 2 plus 2c1, which tells us that 5c1 equals 4, or in other words, c1 equals 4/5. And if c1 is 4/5 and c1 and c2 add up to 1, then I guess c2 is 1/5. So the solution is y equals 4/5 c1 was next to e to the 3t plus 1/5, 1/5 is next to e to the negative 2t. Alright, now let's do this problem over again using the Laplace method. So taking the Laplace transform of both sides, we have Laplace transform of y double prime minus Laplace transform of y prime minus 6y equals 0. And the Laplace transform of double prime is s squared capital Y minus s y of 0 minus y prime of 0. And then Laplace transform of y prime is s y minus y of 0 minus 6 capital Y equals 0. And then if we collect all the capital Y's together, which is what we're solving for, we have s squared y's and then minus s y's and then minus 6 capital Y. And then there's some constants and s's. Minus s, y of 0 is 1, so we've got minus little s, minus y prime, so minus 2, minus minus y of 0, so plus y of 0 plus another 1 equals 0. So if we put all this on the right hand side, we have, let's see, minus s minus 1, So we have s plus 1, and then divide by what's next to y, over s squared minus s minus 6. So that's s plus 1 over s minus 3, s plus 2. Now notice what's next to y here is basically the characteristic equation. S squared for the y double prime, minus s for the minus y prime, and minus 6 for the minus 6y. So this is the auxiliary equation here basically, next to y. So y equals this fraction, and all the pieces in this fraction are things that we could handle if we were to take Laplace transform individually. So let's use partial fractions to separate this out. So we'll write s plus 1 over s minus 3, s plus 2 as something over s minus 3 plus something over s plus 2. Now multiplying through to clear denominators, we have s plus 1 equals, when we multiply through, the s minus 3 is going to cancel, and we have a times s plus 2. And then here, the s plus 2's are going to cancel, and we'll have plus b s minus 3. Alright, so we could plug in s minus 2 and s equals 3. We could plug in s equals minus 2 and s equals 3 and probably solve it that way without having to write out equations. So what happens if s equals minus 2? We have minus 2 plus 1. Minus 1 equals, this whole thing disappears. B times minus 2 minus 3 is negative 5, which tells us that b equals minus 1 over minus 5, 1/5. And then if we try s equals 3, then we get 3 plus 1, 4 equals a times 5. And then this part disappears. So I guess a is 4/5. So y equals 1/5 times, I'm sorry, this is the 4/5. So y equals 4/5 of the fraction 1 over s minus 3 plus 1/5 of the fraction 1 over s plus 2. Then the solution is inverse Laplace transform of y, which is y equals inverse Laplace transform of 4/5 1 over s minus 3 plus inverse Laplace transform of 1/5 1 over s plus 2, which is the 4/5 can come out, and then 1 over s minus 3 corresponds to e to the 3t. The 1/5 can come out. This is e to the 3t. 1/5 comes out, and we have e to the, so this is s minus negative 2. So e to the negative 2t. So that's good. That's the same example we got. That's the same answer that we got last time, which is good because both methods should give us the right answer. All right, let's do another example now, which is non-homogeneous. All right, I'm going to do example 10.4.4 from the book, again with more detail than the book gives. So the question is, what solution of y double prime plus y equals e to the 2t satisfies the initial conditions y of 0 equals 0 and y prime of 0 equals 1. So to start, we take Laplace transform of both sides. So we have Laplace transform of y double prime plus capital Y equals Laplace transform of e to the 2t is 1 over s minus 2. Laplace transform of the second derivative is s squared y minus s y of 0 minus y prime of 0 plus capital Y equals 1 over s minus 2. So if we collect the y's together, we're solving for capital Y. We have y times s squared plus 1 minus s y of 0. Y of 0 is 0, so that's going to go away. Minus y prime of 0 minus 1 equals 1 over s minus 2. So we have y, I'll keep the s squared plus 1 here for a second. Y times s squared plus 1 equals 1 over s minus 2 plus s minus 2 over s minus 2 when we add the 1. So that's going to be s minus 1 over s minus 2. So that means that y equals s minus 1 over s minus 2 times s squared plus 1 on the bottom. Alright, so now I want to take the inverse Laplace transform of y, and we're going to use partial fractions because it's not in a form where we have the inverse Laplace transform memorized. So we have s minus 1 over s minus 2 times s squared plus 1 equals something over s minus 2 plus, now the s squared plus 1 fraction is going to get a bs plus c on top because the degree of the denominator is 2, s squared plus 1. Now if we multiply through by s minus 2 times s squared plus 1 to clear denominators, s minus 1 equals a times s minus 2 is going to cancel with the s minus 2 and we'll have s squared plus 1 plus bs plus c. S squared plus 1 is going to cancel that s squared plus 1 and we'll get s minus 2. Again, notice that what we had next to the y is basically the auxiliary equation, s squared plus 1. That's always going to happen. All right, so s equals 2 would be a good thing to plug in because that would make the second expression disappear. So try s equals 2. Then we have 3 equals a times 5. 4 plus 1 is 5. And that's it. So a, I guess, equals 3/5. So I think that's the only good thing to plug in. Now we're going to have to compare coefficients of s squared, s, and the constant on both sides. And I guess we can plug in the 3/5 for a. So we have s minus 1 equals 3/5 s squared plus 1 plus, let me write this out as 3/5 s squared plus 3/5. And then we have bs squared minus 2bs plus cs minus 2c. So we have 0 s squared plus s minus 1 on the left equals how many s squareds on the right? 3/5 plus b s squared, and then how many s's? Minus 2b plus c. So let me say plus c minus 2b s's. And then the constants are 3/5 and minus 2c. Alright, so if we compare constants, we only have one unknown, so that's going to be easy. So we have minus 1 equals 3/5 minus 2c, which means that 2c equals, if we put that on the left and then add 1 on the right, 2c equals 8/5, which means that c equals 4/5. So we know a and c now. Now we just need b. B is pretty easy because we have 0 s squared on the right, which means that 3/5 plus b has to be equal to 0, which means that b has to be negative 3/5. Okay, so now we can write y as a sum of things that are easy to take the inverse Laplace transform of. So y equals a over s minus 2. So 3/5 of 1 over s minus 2. bs over s squared plus 1. b is minus 3/5 s over s squared plus 1. And then plus c over s squared plus 1. Plus 4/5 1 over s squared plus 1. So that means that regular y, which is the inverse Laplace transform of capital Y, equals 3/5. Inverse Laplace transform of this is e to the 2t minus 3/5. Inverse Laplace transform of this is, so 1 is 1 squared, so it's going to be cosine of t, and then plus 4/5. 1 is 1 squared, so it's going to be sine of t. Alright, that doesn't match what I have in my notes, so I'm looking for a silly error I might have made. Now when s equals 2, oh darn it, I wrote 3 on the left hand side when I meant 2 minus 1 is not 3, but it's 1. So 1 equals a times 5, which means that a equals 1/5. So if a equals 1/5, then it should be 1/5 and 1/5. So that means that b equals negative 1/5, not negative 3/5. And then this 3/5 is a 1/5. So negative 1 equals 1/5 minus 2c. Or negative, so put 2c on the left, and then we add 5/5 to 1/5 and we get 6/5. So c equals 3/5, not 4/5. So changing my multiples here, that's 1/5 minus 1/5 and 3/5. And then 1/5 minus 1/5 and 3/5. Alright, checking my notes. Okay, that makes everything right now. 1/5 minus 1/5 and 3/5. So I guess we have to be careful with those partial fractions and make sure we solve all the equations correctly. The end.